Hi, ch12. So we'll continue with the notes. I didn't get any questions from calculation of oxidation numbers, which we looked at last lesson. Uh, if there's any questions, just make sure, again, you send them my way and I'll go over them um, for the next lesson. Again, just a couple of reminders. Like I said, the previous lesson, there won't be a final exam in the course. What we'll do is we'll finish off this unit, and then I'll give you a take-home unit exam on electrochemistry. And also with the school opening up on Monday, again, all the instruction will remain online. So you won't be missing out on anything if you if you don't come to school. There won't be any new instruction or any new materials or anything. Um, Coming to school is just an opportunity if you are struggling, need some extra help, to come in. Okay, but if you're doing fine and managing at home, there's no need. Okay, so again, just keep sending questions if you have them. Okay, so what we're going to look at now is we're going to determine, based on the materials that are put together, if we're actually going to get a redox reaction occurring. So what we're going to use is the table at the back of uh, the back of the textbook, which says standard reduction potentials, and this is kind of like the acid base table. So on the left hand side, uh, when you're comparing, it has the increasing tendency to reduce or strength as an oxidizing agent. So for example, Ag plus would be more readily reduced than Cu2 plus. Okay, so that's what that means. And then on the going down and looking at the right hand side, this is just the opposite. So this is telling you which has a greater tendency to oxidize or a stronger reducing agent, right? So lithium would be a stronger reducing agent than zinc. Okay, so we're going to need to use that table to look at the examples that we're doing. Okay, so when you look at that table, just be aware that some species have more than one oxidation number. So like for example, if you're looking at copper, there's a copper plus one and a copper plus two, right? So you have to just be familiar with that and make sure that you're looking for the correct oxidation number. Um, you'll notice that these will have double arrows, right? So that means they're reversible, right? There's an equilibrium that can go forward or backwards. Um, when we're looking at a reaction that's spontaneous, then we'll use a one-way arrow, right? So that just means that you start from reactants and you end at products. So that's when you combine the half reactions. Um, Okay, so this is what we're going to be going with here. Okay, this point. If two half cells are joined, the higher half reaction on the table will undergo reduction, and the lower one will undergo oxidation. So I'll show you how we do that. So for example, let's look at this one here. Okay, so you've got copper 2 plus and copper metal. Okay, so that's one half reaction, and then you've got the zinc 2 plus and zinc metal half reaction. So it'd be good for you to have that table open, and what you should find is this one here is higher. Okay, now I can't put these together the way they are because both of these are showing a reduction, right? So this is gain of electrons, this is gain of electrons. So it's saying of these four, which one's going to reduce and which one's going to oxidize. So because the copper 2 plus is higher, that's the one that's going to reduce. Okay, so what we have to do with the one that's lower is we're going to flip this around and and write it in the opposite way. So we reverse the zinc reaction, keep the copper as is, and so now the zinc looks like this. Okay, so your copper 2 plus is going to get reduced, your zinc metal is going to get oxidized. The reason why this one flips around is because it's the lower half reaction. Okay, if we just leave it the way it is, this is basically going to be no reaction. Okay, because the zinc 2 plus will not react with the copper 2 plus. Okay, so this is how you get it into a. We haven't got to the full reactions yet, but this is on our way to writing a complete redox reaction. In order for it to be a complete redox reaction, you have to have one reduction half reaction and one oxidation half reaction, right? That's what redox means. And then we can put this together. Okay, so there's if we know what's going to be coming into contact with each other, then there's basically a couple of possibilities. One is you're not going to get a reaction, and the second is you're going to get a spontaneous reaction. Okay, so there's two ways you can get no reaction. So one way is like the way I was alluding to earlier, is if both reactants are found on the same side. So either they're both on the left or they're both on the right. Okay, because you can't have two reductions and you can't have two oxidations. So if they're on the same side, no reaction is possible. Okay, if they're on the opposite side, you can still get no reaction, and that occurs when the one that is lower on the table is the one that's being reduced. Okay, so the one that's higher on the table is the one that's going to be reduced. And then if the one that's higher is reduced, the one that's lower is oxidized, then you get this scenario here, which is a spontaneous reaction. Okay. So let's look at figuring out what's going to happen here. Okay, so the first one here is Cl2 mixed with Br minus. Okay, so what you do is you look up on your table and you want to find Cl2 and Br minus. So when we find that, we see here's Cl2. It's high, so these are the two half reactions. So I just copied these from the table. Okay, so the Cl2 is the higher one. Okay, so here's your Cl2, and the lower one, here's your Br minus. Okay, and that's what you want. So you want the one that's higher to be your reduction, right? Because this one is going to gain the 2 electrons, and you want the one that's lower to be your oxidation. So what's going to happen to the one that's lower is this one's going to get flipped around, which is what you want it to do, and then it becomes an oxidation, right? So then you get the reduction, oxidation. The lower one is the oxidation, so this is going to be spontaneous. Okay. Let's look at the next one, mercury 2+ and gold. Okay, so there's the gold. Okay, so this half reaction is higher. There's the gold, and then there's the mercury. Okay, so this is like the opposite of question A. So what's happening here is in order to make this work, I'm going to have to flip this one around to put the gold on this side, which means that it becomes oxidized and then the mercury becomes reduced. And that's not going to work because the higher one should be the reduction reaction, not the lower one. And you'll notice on your table that you've got voltages. I'll get to those pretty soon. Okay, and what those voltages are for is when we try to calculate the overall voltage of putting together an electrochemical cell. So essentially a battery. Okay, so this so don't worry about the voltages right now. You don't need to implement them in what we're doing. Okay, so this would be a no reaction. Okay, and the last one here, you got tin and manganese. Okay, so again, I copy these from the table. The tin is the higher reaction. The manganese is the lower one. The problem here is you notice they're both on the same side. Okay, and so because they're both on the same side, this is going to be a no reaction because you can't have two oxidations, right? Because they both need to be flipped around in order to react. Okay. So what you're going to be doing today is basically just looking at the table and then trying to figure out what's spontaneous, what's not spontaneous. And again, you need to know what reduction and what oxidation mean in order to do this. Okay, so I'll stop there. So I'll get you to work on these questions here, page 199, 7 to 18. Okay, so get these done for Monday, and just let me know if there's any of these questions that you'd like me to go over. I know sometimes when you look in the back of the book, it doesn't really make a whole lot of sense, so I can definitely help out with that. Again, like I mentioned before, no final exam. and the school time in actual real class time is just intended for students who need extra help or struggling with something that we've covered before. Otherwise, you don't need to concern yourself with that. Okay, so I'll stop there. So continue to stay safe, and I'll talk to you again on Monday. Okay, bye now.